So in our application to the game of Hearthstone, we use the UCT enhancement to the determinized Monte-Carlo tree search. So the algorithm we use is determinized usually like duct for short. And we also another modification we did is instead of like doing the full rollouts, we actually cut the rollouts at the depth of D and call the entrance state evaluation function, surface entrance state evaluation function, and the back value up instead of like doing the full rollouts. And we also use the surface move generator to generate the moves in both the in-tree and the simulation phases. And for this algorithm, there are 3 parameters to tune. The first one is the expression constant C in the UCT formula, and the other 2 are the number of words and the rollout depths. But even though we fine-tune the algorithm, there's the algorithm actually still. Sorry. Sure. Because I haven't like. There is some connection issue. This is actually the PowerPoint, so maybe I can try to use. Okay, sure. Sorry there might be some connection issue. Okay. Okay, sure. Actually, I already. Maybe I'll just use the PDF to show. Just go up. Yeah. Yeah. But I'm afraid it will just go to. Yeah, we're from here. Okay. Okay. Okay, it works. So. Maybe it's better to. Maybe I will just use a PDF here. I have opened a PDF version. Maybe use this one.
Just full screen this.
Yeah. So I'll just show this one. Oh, this one might work. Okay. Sorry for the delay. So there are so even though we can fine tune the search algorithm, there are also problem of like frequently chance events happens in the game. So especially for the card drawing chance event, which happens at almost every turn, and the card drawing chance event branch factor can be very huge if we have like more than 1 cards to be drawn in a turn. So, despite the number of the branch factor is large, there are those outcomes of the chance events can be quite similar, and we can actually bucket those similar chance outcome into together, and after doing this we can do a few samples in those buckets, because the samples in one bucket are highly correlated and similar. So we can just reduce the branching factor by doing pre-sampling and taking n samples in each bucket. So the sampling criteria is quite simple. It's based on the observation that similar cards, the cards with similar mana cost has similar values. It's because of the reason of the game balance. And we also try some other bucketing criteria. It turns out this simple bucketing criteria works the best. And empirically, this is the bucket we use for the decks we tested in our experiments. And we find out that given the limited search time budget n equals 2. When one card is drawn and n equals 1, when more cards is drawn, it works the best because it balances actually the efficiency and the quality of the sample. So the experiments we first run experiments to fine tune the parameters. So there are 3 parameters to tune. Instead of like running a full 3D grid search, we actually select a candidate pool by running small scale experiments, and then we run round robin tournaments between each pair of candidate configuration, and then in the end we find out the best configuration will be C equals to 0.7, number 4 equals 10, and the depth equals 5, which is under the given time budget equals to 5 seconds. And then we run the experiments of the fine-tuned duct versus against the fine-tuned duct with the chance of bucketing. And this is a result of of the improvement of adding the chance of bucketing into the duct, and we can see there is an improvement in all the 3 matchups. And the second part of the of our improvement is to learn the high-level rollout policy in Hearthstone. So another observation in the game of Hearthstone is it can be also applying to some other video games, like there's an action hierarchy in Hearthstone. If we consider like choosing card to play as a high-level action, so choose a target for that card and choosing a target for minion can be considered as a low-level action, because those are kind of similar to, that is, choose a target for a source. So in this case, our goal is to try to find which card to be played at each turn. So actually, in real human plays, human players will spend like almost 90% of the time of a turn to consider which card to play, and just 10% of time left to execute those plays. In this case, we define our training targets, which is called turn card set. So which is actually the card to be played in the turn, starting with the state M, and it is actually represented as a 1D vector. Each element in that vector will represent a card. So if a card is going to play the corresponding bit will be 1, and if this card is not played, the corresponding bit will be 0. And our goal is to train a network that can receive the state features as input and pop out the card probability vector. So the training data, we actually use the open-handed training data with UCT agent plus the silverfish end-to-end evaluation and the chancellor bucketing with 10,000 rollouts. And we actually generate, for each mirror games, we generate 27,000 open-handed games, and there are in total 4 million training data. So the reason of using open-handed rollout replay is because the open-handed games, the UCT can figure out the counter plays to counter opponent's hand, and also because we use the determinization in our search algorithm, it can be applied to our search algorithm because we assume we know opponent's hand. And the state features, so the idea of applying learning into the state features is we want to learn from the role features. So in Hearthstone, as I mentioned, that Hearthstone can be decomposed into different parts. So there are 3 feature groups. The first one is global, the second one is like board feature, the third one is hand feature. So global feature is quite simple. They're just a one-hot encoded, it is represented as a one-hot encoded vector with these 4 features. And hand feature is kind of a little more complicated, that each column, each card appears in a certain matchup will given a index, and the index is given by sorted the card first by this card type and then by the mana cost. And then each row here will represented by represented as a feature related to each card, and the hand feature will represent it as a 2D vector, and but it can be also flattened into a 1D vector. The board feature is a little bit more complicated. That instead of like for each meaning, instead of like we have one index for each meaning, we have a 2D index. That is, it has a index for its card. It also has an index for its current health point, and after this we use several planes to represent features related to actually those are binary features related to each meaning, and these are the features we use. So all the features are raw features. Just one exception is the total attack greater or equal to the enemy's total board HP. And we try different network architecture to try to capture the locality patterns of the features of the feature space. So the first architecture we tried is the convolutional neural network architecture. So three different features of the three different modules are fed into three independent networks, and then after followed by several convolution and pooling layers, we concatenate those output of the three independent networks into a flattened layer and followed by two fully connected layers, and the output will be the probability of each shot to be played, and the loss is the logistic loss. And we also have a shallower, and there's no convolution structure there, but this network is trained for faster real-time evaluation, and the structure is similar. We have like three independent subnetworks at the beginning, and then concatenated by concatenation layer and the two fully connected layers. So the experiments we run for those card play networks is, first we want to see how well it can predict the card to play in a turn, and second we want to see how well those networks can do in player games independently. And the third one is we want to incorporate those networks into Monte Carlo research to see if there's any improvements. So first one is the TCS prediction. So we actually have these predictors we have those predictors to predict the test set generated by the open-handed UCT player. So the first one is the card play networks. The second and second one is the original Silverfish UI, but with less time constraint. And the third one is the greedy accent chooser according to the heuristics. So here is the prediction things. It is not a surprise that actually the CNN with 1.75 million parameters works the best, and it's actually quite surprising that the shallow networks also predict very well, like against the Silverfish, because it's almost on par with Silverfish. But we also tried some more complicated network structure, but it didn't perform better than the first one, because maybe it's because of the overfitting issue. And the second one is we play games by using the best performed CNN there. So the algorithm for this combined agent is quite simple, because the card play networks can only choose card play, but it cannot choose which target for the card. So we actually combine with a greedy low-level action chooser with a heuristic function, and we repeat this until there's no actions available. And here is the result of the combined agent, and actually it's quite exciting that it's on par with this one-turn search-based Silverfish, even though it lost badly to the like 3-turn search-based Silverfish. All the games are open-handed, so it's kind of unfair, but the card play network can only play open-handed games. And the last one is incorporated these networks into the Monte Carlo tree search. So we actually, the old policy, even though it is uniform random from the actually promising moves, but there are still some drawbacks of like old policy also still suffers from making mistakes. So we actually we test a different network architecture, but the CNN turns out to be too slow to incorporate into the rollout phase. So we actually use the DNN to replace the rollout policy. So we actually define a multi-level rollout policy. So so the algorithm is also simple. So we choose a level randomly first, and then because the output of DNN is actually the probability of each card to be played. It's not a distribution, so we actually turn it into a distribution by applying a temperature softmax function, and also we also like to choose the low level action. We also apply a tuned softmax to the normalized heuristic value, and so the most improvement is on the hand warlock deck. So so probably it's because of it actually avoids some fatal mistakes in the original uniform randomly rollouts, like in the hand warlock deck. So they will just play some like self-hurting spell without any purpose in the original rollouts. So to wrap up, so we have in this paper we have like two improvements. So the first one is channel bucketing on the duct algorithm, so which solve the problem of the search algorithm just stuck in the large chance branch factor node. And the second is we actually learn the high-level raw policy by generating the a huge amount of data from the Monte Carlo research player, and we apply those networks to play games, and also it helps to improve the strength of the Monte Carlo research. And the future work can also be doing the improve the inference AI, because now it's uniform random sample from the information state, and we can also improve the chance event bucketing strategy, because this one is based on the expert knowledge, but there can be some like statistical method to clustering those buckets. And we can also try to improve the entry and the low-level policy by learning. And also the reinforcement learning, like interleave the reinforcement learning can also be applied into the game of Hearthstone. And we are considering to migrating to another engine to get, because for this engine it's not updated anymore, so we need to like add those features ourselves. So yeah, that's it. Okay.
I gave you score time because of the slide.
Thanks. Yeah.
Thank you. Any questions for the team? And also, like, please use the microphone when you ask questions. All future speakers use the microphone when you speak. Here you can adjust the height of it. We're getting complaints from your.
Thank you for your presentation. I have a question and a comment. So the question is, if I understood correctly, your system can only play with open hand, so it has to know the hand of the adversary to play the game, or not?
The networks can only play open hand game, but if we incorporate into the DUCT algorithm, so it can play closed hand game, because in the determinize UCT algorithm will just sample the word in advance. So yeah, so in some sense you are correct. So the network can only play open hand game. Yeah.
Okay. So the comment is, this is the second work presented on artificial intelligence for Hearthstone, and an interesting thing is that the AI of the bots, which we compete against, is still better in the end. So you were beaten by the third play, and in our work we were also not able to win convincingly against the IE of the simulator. So they are still a little bit ahead of us, and maybe we hope that next year we can beat them.
Actually,
those AI, artificial intelligence.
Yeah, so actually, I think maybe the AI from the Metastone is slightly stronger than the silverfish, maybe, because I also checked this Metastone, but kind of the limitation of Metastone is that to perform Monte Carlo tree search is kind of slow, so I can only run like 1 or 2,000 of simulation. So the strength of Monte Carlo tree search I tested in Metastone is slightly weaker. In this one, I can run like over 10,000 simulations. So that's that might be the difference. So yeah, so I'm considering like migrating to Metastone. Maybe I will just I can test.
It will be interesting because then we could compare our results.
Yeah, definitely. Yeah, okay. I'm looking forward to this. Yeah.
Yes.
Thank you.
Just a quick question. You used determinization.
Yeah.
Did you think about using information set MCTS instead? Would that have been possible? Or?
Actually, the determinized UCT I use here is the actually in between of the like the fixed number of it's actually a special version of the information set UCT because it fixes the number of the states, right? So if we sample a state at each time, it will be equivalent to the information set UCT, right? So I think for Hearthstone, for this game specifically, in my experiments, I think fix the number of the worlds is sufficient to for the game. So maybe because like if we use like information set UCT, we're going to explore actually the potential branching factor of this tree will be kind of enlarged because you are going to explore all the possibility of the world, right? And in Hearthstone, there are like a lot of world will have very high correlation there. So given limited time budget, the 10 worlds will be kind of sufficient. But if we have more time to search, I think maybe information set UCT will outperform the determinized UCT. I think so. Yeah.
Okay. Thanks.
Yeah.
I think in the interest of time here, so we'll give you a second round of applause. Yes.
Thank you. Thank you very much.